So what we have here is our multi-degree of freedom robotic arm that we are controlling via MATLAB with a simulation. For reference, we've set up a grid. This is positive X, this is positive Y, negative X. The robot is centered over 0, 0, and each of these are 1 centimeter spacing. So from this position, we've defined through the inverse kinematics 4 positions that we want to move to, and we're now going to move through all 4 positions. The first position is going to be
X equal to 15 centimeters, Y equal to 26 centimeters, and Z equal to 3 centimeters.
Okay.
So it's basically the first quadrant at a height of 3 centimeters for picking up stuff.
All right.
So if you can see here in MATLAB, it is asking for the location number, which location you want to move. So I'll just enter location 1. And so it will start at position 0, that is along the x-axis.
So here we are getting ready to move to position 1. You can see the robot moving, and then here is the simulation.
It moves along with the robot, just
so
simulating the exact
You can see
situation.
they are nearly synchronized. Next we're going to move to position 2.
So here you can see the trajectory of motion of the end effector, and it resembles the same as that of the robot in actual place. Now it's asking for the next position to go, so we'll move to position 2, which is X equal to minus 15 centimeters, Y equal to minus 9 centimeters, and Z equal to 24 centimeters. So it's basically quadrant number 3, trying to hold up something in the air above. So we'll go for position 2. So first it sets itself at 0 location, that is the x-axis. Don't move it, it's okay. And again, you can see in simulation as well as in real, both are going to the same location.
And there's a slight difference here because the servo here at the base doesn't have the same range of motion as the simulated robot, so the workaround to get to the same position in space.
So the trajectory might seem different, but the end location is the same, so you're reaching the same point in the space, but it reaches it in a different way.
And so here we are in the 3rd quadrant at a height of
24 centimeters. So in the simulation, what it shows first of all is it marks the location to reach by pink color, and then when it reaches it becomes black.
Now we're going to move to the 3rd location,
3, which is X equal to minus 12 centimeters, Y equal to 21 centimeters, and Z equal to 21 centimeters, which is basically quadrant number 2. So now I'll enter just 3. It will first go to its 0 location, that is x-axis, and you can see that it started moving in the simulator as well as in actual model. You should show the simulator as well.
Yeah. And so right now the MATLAB is solving the inverse kinematic solution to this numerically to get to these positions.
And you can monitor the values of the angles that it's going in real time. For each iteration, it shows what angle the actual robot is going to be at. Alright, so now for the final location, we are going for location 4, which is X equal to minus 27 centimeters, Y equal to minus 16 centimeters, and Z equal to 8 centimeters. There's location 4, and we will move again to position 0. And slowly it will start moving. So if you can see in the MATLAB simulation here, it marks the position by a pink colored dot, and then the robot moves towards it.
So we're not moving as fast as we could. We've slowed the robot in the simulation down quite a bit because the high torque of the motors causes the robot to
get unstable. So we're just moving them slowly with the motors. Here you can see in the simulation window all the 4 locations and the trajectories, how the robot reached there. And the program runs in a loop, so if you want to go to another location from here on, it just asks for a location number, so you just enter the location number and the robot goes there.
Also noteworthy is how we're controlling the robot. We've got USB providing a serial link from MATLAB, and then there's a microcontroller, which is in this case an Arduino Uno, and that provides the pulse width modulation for the servos and reads from the serial port. And then here we have each of our servos in order from the base here to the most distal joint, and they're just receiving standard pulse widths, and only moving to where MATLAB tells it to move.
Alright, so here I'd like to talk about the code a little bit. So the MATLAB code, what it basically does is it's divided into several parts. It starts with initializing the arm, like setting up the servos and having each pins connected to each servo on the Arduino. Then it takes the robot to the 0 position to start it with, which is actually the x-axis. Then we have a few locations predefined for the sample. Then comes the section for forward kinematics. This is where we derive the T matrix using the link lengths. These are the individual A matrices for each and every joint. Then comes the part for inverse kinematics. This is where we have used a numerical method to take care of the inverse kinematics because we had 5 joints. This is how we get different thetas of all the joints. And then we cross-check for the correctness of the thetas because there are always 2 angles possible when you're using a tan function. So once all the thetas have been derived, I'm checking here if the end effector position is matching that of the actual end effector. If it doesn't, then we take the other angle value. This is a simulation plot which takes care of the animation of the simulation, and along with that we are also updating, that is sending data to the robot step by step. This is where we send theta 1, theta 2, and so on. So you can see that each step in simulation corresponds to a specific step in the actual robot working. And then it just goes into a loop and asks you for another work position. So this is how the code in MATLAB works.